So, looking at this, looking at our square roots, whenever we're trying to graph something like square roots, that's when we start with a parent table. To start with our parent table, we take our most simplified version, the simplest, middlest part of it. The parent function for a square root comes from the square root of x, just the x, and only the x. Where we picked some x values to find y values. Square roots was one of our weird ones because we picked x values that were easy to square root. So we typically used 0, 1, 4, and 9 because it gave us y values of 0, 1, 2, and 3. So getting that parent table is the first step. From that, to get our transformations without graphing that, necessarily, sometimes we do graph it, but this time we're not. We take our x plus the h value and our y times a plus our k value, which means we need to know our a, h, and k. So on square roots, our transformation form was our a square root of x minus h plus k. So what transformation do we have here in the one that we're graphing right now? I only see one number, so we only have one thing. H. What's our h value? H is -2. So the only thing we're going to do is we're going to change our x column. So we're going to take all of our x's and subtract 2. So we're going to have -2, -1, 2, and 7. Good at thinking in my head. And since we don't have any a transformation and we don't have any k transformation, the y values are just going to come on over. We're going to have our 0, 1, 2, and 3. These give us our points that we're going to plot up, our -2, 0, -1, 1, 2, 2, and 7, 3 is just off my graph, but it's right about there, and we can estimate that. Ooh, way too chunky. And we're going to get a graph that looks kind of like this. So the other pieces we were asked were our domain and range. So remembering that our domain has all to do with our x values. What's the rule our x values have to follow for this particular function? Where are my x values all living? What's my smallest x value? -2. What's my biggest x value? Does it stop at 7? I heard 7. Does it get to 7 and then we stop here and it never goes any bigger? No. What's the biggest it's going to be? Infinity. So this goes from -2 to infinity. So we write it like this. How about my range? What's my smallest y value? 0. I heard it. What's my biggest y value? Infinity. So it's been a little minute since we've done domain and range. But since we had graphing as our bell work, I wonder what we're going to be doing today. What? Who'da thunk? Okay, so what we're going to do today is we're going to actually start graphing exponential functions. Shock of all shocks. So those pieces that we've been working with, those things we've been doing, we're going to work on graphing those today. And it's going to feel a little bit weird. So, this is where we're going to start. We're going to start with just graphing 2 to the x. So we've got a base of 2 and an exponent of x. And the one thing about exponential functions, it's a little bit weirder than we've ever meant with before, is that our parent function is going to change for every graph that we do today. Because we don't have just an x down in our equation. We don't have like an x squared or square root of x or anything like that. My x is my exponent. So we have to make a parent function for every single base. So that's what we're going to focus on today is these parent functions, because we're going to have more than one. And we're going to figure out what these look like. So we're going to make a table. We're going to try and graph 2 to the x. And I'm going to make a big table. I'm still going to get that good view of the center. So when we pick our x values to find our y values, I still want to get a good view of the middle of my graph. So I still want to have that kind of center 5 that we've used for most everything we've done before. We want to go from -2, -1, 0, 1, and 2. For the most part, we're just going to use these 5 anyway. But so that we can see the graph, I'm probably going to go out a little bit farther so we can see what's going on. So more often than not, we're just going to have these 5. You can always do more, but those 5 give you your best view on our parent table. But we might need a few more just to see what is going on here. So what we're going to do is we're going to come in here and take our 2 to the x, and we are going to probably type it into the calculator, unless we really remember our exponent law is really good, to figure out these values. Because what we're needing to do is to do 2 to the x is we're going to take 2, my base, to the -2. That's my x. I'm going to wait for our lovely announcements.
We did testing continued. Students testing this morning should head to their testing room. Thank you.
So 2 to the -2, and you can type that in our calculator if we don't remember what that does. 2 to the power of -2, and we're going to get 1/4, or 0.25. I don't care if you do decimals or fractions. I'm going to put 1/4. Same thing with the next values. We're going to do our 2 to the -1. 2 to the -1 means it flips as a fraction, so we're going to have 1/2. And again, you can type that in the calculator. We have the tools. They're not being covered by other things. 2 to the -1. The next one we're going to have is going to be 2 to the 0. What is anything raised to the power of 0? Not 0. 1. Absolutely everything. Anything raised to the power of 0 is 1. Then we have 2 to the 1st. 2 to the 1st is 2. And our bottom one here is 2 to the 2nd, or 2 squared, which is 4. So we might be able to see what's happening from this much. So let's plot these points up here so that we can see. Got our 1/2 and our 1/4. Got our 1, 1, 2, and 2, 4. Okay, not too bad. We can kind of see what's happening here. It's going up for surezies on the right real fast. I wonder what's going to happen as it goes farther to the left. Is this going to continue and go down like this? Or is it going to continue off straight? So it might help us get a couple more values to see where this is going to be and see what's happening with our values. So if we look and see what happens at, I don't know, maybe x of negative 3, just to get a few more values to see what's happening here. 2 to the power of negative 3 gives us 1/8. 2 to the power of negative 4 is going to give me 1/16. Then we'll get 1/32. We'll get 1/64. And we can keep going and going and going and going and find some dots to connect this up. The one thing this can never be, is there any exponent that I can put onto a 2 that will make this sucker go negative? Will this ever be a negative value? No. There is an invisible wall. That's right here. On our parent functions, it's right here. There's an invisible wall that the graph can't cross. Because there is no exponent that I can raise 2 to make this be negative. And we're going to talk about this invisible wall here in a minute and what its name is, but I have it like a formal definition I want to give you. So these are what our exponential functions look like, and this one is very clearly exponential growth. As we read it from the left to the right, it is getting bigger, it is growing. We can also see that from our base. Our base is bigger than 1. What is our domain on this one? What are our x values that work? What's our smallest x value that works? I was like, does it stop at negative 4? Could I keep going? What's the smallest it can go? Infinity. I can go all the way to negative infinity. How about my biggest x value? Infinity. So this has a domain of all real numbers, or from negative infinity to positive infinity. How about our range? What's my smallest y value? 0. But does it ever actually get all the way to 0? Or it's just going to get really, 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 really close? It gets really, really, really close. So what we're going to do is we're going to put a parentheses on it like it's an infinity, because it never touches that 0. I'm not going to be super petty about that, but things like SAT definitely will be. So you guys have just graphed your very first exponential function. And it's one of our parent functions. And what we're going to talk about on the next page before we go do a few more of these graphs is that invisible wall we have, where this can't go negative, so it's got a wall here, and it has a special name. But any questions on this before we go talk about that for a second and then come back to graphing? Okay. The wall is called an asymptote. It is a line on our graph which our function cannot cross. It is a wall. The graph will come up to it, cannot go through the wall. I can get really, really close. I can pretty much touch it, but I can't go through that wall. My lines cannot cross those asymptotes. So when we find an asymptote, it's a wall. Don't go through it. Okay? Asymptotes are walls we cannot go through. We are going to have asymptotes in, I think, pretty much every function we do from now to the end of the year. So asymptotes are going to be a big thing for us. And it is just a wall our graph cannot touch. It can't go through. So for all of our exponential functions, they're going to be horizontal lines, which means they're going to be written as y equals whatever our k transformation is, which when we get into our transformations, I'll talk about that. But so our asymptote is going to be written as a y equals for right now. That is not true of all asymptotes. That is just true of these asymptotes. So we're going to do a couple more parent functions, and we'll start talking about transformations. Because I can't use my parent function for something like 2 to the x when I have a function that's base of 3. Base of 3 makes it a different parent. So if we ever have a 3 to the x, we have to make a new parent function. So it's not quite as straightforward as when it would be parabolas. So if we do 3 to the x, I have to make a new parent function, which means I'm going to make myself a new parent table. And what we're going to do is we're going to do this without doing more values. I'm only going to do those center 5. So I'm just going to go from -2, -1, 0, 1, and 2. Because yes, you can do this by picking a bunch of values and plugging a bunch of them in and finding a whole lot of information, but it's going to take you a really long time if we do that for every single one. So I'm going to take just these 5, and we're going to get our parent function from here. So then what we're going to do is we're going to evaluate our 3 to the x at these values. So we're going to take 3 to the -2. What is 3 to the power of -2? 1/9. Absolutely right. 1/9. What is 3 to the power of -1? 1/3. What's 3 to the power of 0? 1. Anything to the power of 0 is 1. You'll notice this on all of our parent functions for this chapter. This middle is always going to be 0, 1. All the parent functions will have that. Then we have 3 to the 1st, which is just 3, and 3 squared, 9. So when we plot up these points, we're going to wind up with some really small fractions here, and that's okay. My 1/9 and my 1/3 are going to look obnoxiously similar. We're not going to bust out rulers, do anything crazy, trying to get it to be perfect. We're going to get it close, and that's going to be good enough. So we've got our 1, 3, and then my 2. 9 is way off the board up here. You can even just draw like an arrow saying it's going to be up there somewhere. And when we connect this up, I want us to remember this has one of those invisible walls. So instead of plugging in a whole bunch of other points, I'm going to remember that this has an asymptote right here, which means my function cannot cross that line. So when we connect up these points, I need to not cross that line. It's okay to get a little closer than that. I don't like the way I did that. Like, it's okay to get close to it, but we cannot cross it. So the way we can mark that down, that place that this is never going to cross, is we're going to list this as our asymptote with an equation. On all of our parent functions, our asymptote is going to be at y equals 0. Every single time. I have no idea why I put it in that exact location. I'm going to put it down here just a little further. Y equals 0 is our asymptote. Parent functions are always going to have an asymptote at y equals 0. All of the parent functions, that's not going to change. So then our last piece on this one is we're going to think about our domain and range. What is our domain going to be on this one? Negative infinity to positive infinity, or all real numbers. I'm pretty sure I heard all real numbers, but it was super quiet. How about our range for this one? So it's going to be from 0. What's my biggest? Infinity. And our range on exponentials is always going to have your asymptote in it. Whether it's above or below the asymptote is another question, but it will always have the asymptote in your range. The k is going to be involved somewhere. Okay, I'm going to toss one funky parent function at you before we get into some transformations. Because sometimes they're going to give us fractional basis. And since we have calculators with us, we can absolutely do this with our calculators and do it fractiony. So option 1 is to just straight up do it the way we've done everything else so far today, where we pick our x's to find our y's using our -2, -1, 0, 1, and 2, and knowing that we're going to have an asymptote, since this is a parent function, at y equals 0. And that's how we're going to start this. We're going to do it just like this, and we're just going to be really careful. So we're going to take the fraction 1/2 and raise it to the power of -2. So when we do that in the calculator, we need to be super duper careful, because we're going to take our fraction 1/2 and raise it to the power of -2. What we wind up with is +4. We're going to take our fraction of 1/2 and raise it to the power of -1. And again, when you go and do that in the calculator, and we are super careful, we get a +2. anything raised to a 0 power is 1. 1/2 to the first is just 1/2. And 1/2 squared is 1/4. So if we look really carefully at these values, they're really, really close to other values we've seen. It is, in fact, almost identical to our 2 to the x if the x's had the opposite sign. And that's exactly something you can do. If you do not like dealing with the fractions, you can do like we did when we're solving and rewrite this with a different base and do this as 2 to the minus x. That's another way to think of this. They mean the same thing. So 1/2 x and 2 to the minus x are the exact same thing. So 1/2 x and 2 to the x are related. They're just not super identical, so we just got to be super careful. So when we plot these up, we're going to wind up with our first decay of the day. -1, 2, 0, 1, 1/2, and 2 1/4. And we're still going to have our asymptote at 0 because this is a parent function still. So it's going to, give me a second, look something like this. So our last piece on this one before we start going into some transformations is we're going to notice our domain and range. What's our domain again this time? All real numbers, or from negative infinity to positive infinity. Both are fine. How about our range? It's still 0 to infinity. Or again, if you like the algebraic, our y's have to be greater than 0. And our parent functions will never be negative. They will never be negative. They are never going to have negative values on this side. So our parent functions on these ones take a little bit of time to get used to. But once we get used to writing our parent functions down, our transformations are so much easier because after that, it's 100% the exact same process as every other time we have graphed this year. Because what we're going to do is we're going to look at a transformation of 2 to the x. So we've already written this parent function once. And I keep trying to write stuff in that corner, and it just does not work. I always forget about that. But the important piece we need to have next is we need to have our transformation form, which I'm going to rewrite this. I'm erasing it right now, but it was just right underneath the close button. So our transformation form for these functions, we have our a times our b, which is our base. That's the piece for our parent function. The exponent is where we have our x minus h, and then plus k is down here. So we do have a new letter here, but b is just our base. Oop. So b to the x is always going to be your parent. So this tells you everything else. So the parent function is not a transformation. It's the starting point. So on this one to the left, over here, our g of x, we have a base of 2. That just means our parent function is 2 to the x. It's not that it has an a value 2. It is not anything else with it. That's not a transformation. This is our parent. So we're going to use our parent table that is 2 to the x, where we picked our x's and found our y's using those base 5 values we've used before. And our parent functions always have asymptotes at y equals 0. So our parent function, this is the very first one we did. 2 to the minus 2 was our 1 over 2 squared, or 1 over 4. 2 to the minus 1, that's 1 over 2. Anything raised to a 0 power is 1. 2 to the first is 2, and 2 squared is 4. So that's our parent table. We're going to use that to make our transformation. To get our transformation, we are going to do a table just like we've done for the bell work and for the last couple of chapters, where we take our x plus h and our y times a plus k. Same transformation form. So we've got to play match them up to know if we have a's, h's, or k's. So our h, again, still has that opposite sign and is in the exponent. So what is our h value on our function over here? -1. So our h, ooh, that's not a pen. There we go. Our h is -1. How about our k that's added on the end over here? -3. Our k equals -3. So just like we've done with the last few graphs, the ones we've done before, we're going to take our x values from our parent function and apply our h transformation. We're going to take our y values from our parent function and apply our y transformations. We do not have an a value here, so we're not going to do anything with it. So all we've got to do is this addition and subtraction. So I'm taking my x values. I'm taking my -2, and I'm going to subtract another 1. So we're going to have -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0, and 2 minus 1 is 1. These fractiony ones, we're going to need to be careful because they're not particularly pleasant. We can also use our calculators if we need to when we have 1/4 minus 3. We get -2 3/4. Or -2.75. I do not care if you use fractions or decimals. I do recommend mixed numbers as opposed to an improper fraction. But I don't care if it's decimals or fractions that you do. If we do 1/2 take away 3, we get -2 1/2. 1 minus 3 is -2. 2 minus 3 is -1. And 4 minus 3 is 1. Our last piece I want to write down before we plot stuff is we are always, always, always going to have our asymptote at y equals k. So our y equals -3. before I plot my points, I want to draw in that asymptote. So I'm going to make my whole table, write down my asymptote, and then graph stuff. So where y equals -3 starts on my 3 here down here at the bottom, and it is a horizontal line. This is that wall. I know it cannot cross. It can come real close, but it can't cross the wall. Can't go through it. So when we plot up the rest of our points, we're going to see what that looks like. So we have -3, -2 3/4. So we are just barely above this wall. -2, -2.5, -1, -2, 0, -1, and 1, 1. And we are going to wind up with a function that looks like this. We've already identified our asymptote. It's y equals k. It's always going to be our k transformation. What is our domain? All real numbers. What is our range? Last question for the day. -3 to infinity. It's always going to use our k value. Every single time. Okay? So they're a little weird. We have a new word to get used to. Things are a little bit different. But we use the same process as we've done before. This is part of the reason we have graphed everything with A, H, and K. So when we get to stuff like this where we need it, we're not going, what even is that? Because A, H, and K are familiar. We've used them before. We have used these transformation tables before. It's the graph that's weird, not the entire mechanism. Okay, so I have these 7-4 worksheets up here. I will pass those out. We are going to have chapter tests at the end of the week. This is the last homework of the chapter. We are going to do some more graphing tomorrow. They don't get worse. Like, they're getting A's, H's, and K's. But they're not worse than we've dealt with before. Okay? So those. And then we should be about 30 seconds away from the announcements starting.